So today we're going to extend the idea of complex numbers to the concept of quaternions. Now, quaternions are, I've been saying all along that quaternions are complex numbers under the hood. And so today I'm going to explain what I mean by that. But I just want to show you this image here. This image here is actually a three-dimensional Julia set. Okay, this is a quaternion Julia set. This was generated using quaternions instead of two-dimensional complex numbers. So as you can see, you've got these like curvy things going on and a kind of a slice where you can see the Julia set. Now, many years ago, I used quaternions to generate this 3D model. Now, this 3D model is, basically identical to this picture here, only it's closed up. It's closed up, so you only see the surfaces. And basically, if you took a two-dimensional slice out anywhere, if you took a two-dimensional slice out of this model here, inside it would be kind of like a geode. It would be there, you would be seeing a Julia set inside. So if you slice this in half, you would see a Julia set on the inside. So, quaternions are really interesting. They're, the fact that you can use the same formula, the Mandelbrot set formula, the Julia set formula, to generate three-dimensional fractals and four-dimensional fractals, which are almost impossible to visualize, I find really interesting. And of course, the main reason I even got interested in complex numbers in the first place is because of the Mandelbrot set and the beautiful images that you can generate using complex numbers as iterated by the function z equals z squared plus c. So right off the top, the main difference between a complex number and a quaternion is the complex number has two terms. It has a real term and an imaginary term, and quaternions have four terms, a real term and three imaginary terms. Okay, so the three imaginary terms are identified by I, J, and K. So that is the main difference between complex numbers and quaternions. Of course, the original complex number is in the quaternion, which is one of the reasons why I say quaternions are complex numbers under the hood, because there it is right there, but it's got these additional terms, and it can be represented as a 4x4 matrix. So complex numbers are basically two-dimensional numbers, and quaternions are basically four-dimensional numbers. So complex numbers, as I said, are two-dimensional numbers, but these two-dimensional numbers have very specific rules. Okay, so here's the equation. So usually complex numbers are written using C equals A plus BI. Technically, there should be a 1 in here or an R in here for the real identity. The R and the I are the identities, and the A and the B are, I'm going to call them parameters. Okay, so A and B are the actual numbers like 2.5, 3.6, 0.00001, and the R and the I are the identities. Okay, the identities are where you have zeros and ones in. So here are the identities of the complex numbers. So the identities are where you have where you have ones in certain positions in the matrix and zeros in the rest of the matrix. And so in complex numbers, 1, this is how you write 1 in complex numbers. The forward diagonal with ones in it is the identity matrix, the positive identity matrix, and -1 has -1s on the forward diagonal, and positive I has a 1 in the upper right hand corner and a -1 in the left hand corner, lower left hand corner, and -I is the opposite, where you have -1 here and +1 here. And so these are the four identities of the complex numbers. And so the specific rules for complex numbers are as follows. Okay, so I squared is equal to -1. And -1 in two-dimensional numbers has the -1 on the forward diagonal. Okay, so when you take this I here, when you take this matrix here and you square it and you multiply it by itself, okay, you end up with -1s on the forward diagonal. And this is one of the main rules of complex numbers, is the imaginary number squared is equal to the negative identity. And of course, there is another rule, which is this rule right here. Is kind of an unspoken rule because everyone knows that it's true. It really should be written down though, where r squared is equal to +1. And so that is the case where, so in this case, 1 squared is equal to 1 and -1 squared is equal to 1. So in both of these cases, so this is one identity of the real numbers, the positive identity of the real numbers, and this is the negative identity of the real numbers, and the r squared, so 1 squared is equal to 1. You'll have 1s on the forward diagonal, and -1 squared is equal to 1. You're going to have 1s on the forward diagonal. So for completeness, I would have to add that as a rule. And so r squared is equal to 1, which is 1s on the forward diagonal, and the imaginary number squared will have -1s on the forward diagonal. And so those are the rules of complex numbers. And when you have two-dimensional numbers, when you're representing complex numbers as two-dimensional numbers, I had to add an additional rule. Okay, so I am adding an additional rule where the forward diagonal, the elements on the forward diagonal have the same sense. So either they're both positive, or they're both negative, okay? And the backward diagonal always has the opposite sense. And so either it's going to be positive here and negative here, or it's going to be negative here and positive here. And so these are the complete rules of the complex numbers when written in 2x2 matrix format. So quaternions, instead of being a two-dimensional matrix, so instead of being having two rows and 2 columns, quaternions have 4 rows and 4 columns. Okay, so it's a 4-dimensional number. It's got 4 elements. It's got a real and 3 imaginary components, and the quaternion itself in matrix form is going to have 4 rows and 4 columns. So the trick here is trying to figure out what to put into, what are the identities of the quaternions. So in complex numbers, we know, so in complex numbers there are 4 identities, 2 positive identities, and 2 negative identities. Okay, so for quaternions, I expect to find 4 positive identities and 4 negative identities. But before we do that, I want to give you an idea of what I expected to find. Okay, so this was the first time I was doing this in matrix format. I've done quaternions before using algebra, using other methods, but this was the first time I decided to delve into it and come up with the 4x4 matrix solution. And so I thought it would be fun to try and do this from first principles, and so that is what I did. So I just want to kind of show you, there's a little bit of a fractal scaling here. So here's the no matrix, and then here is a 4-element matrix, and then there is an 8-element matrix, and you can imagine that there could be, this could keep going on, and you could get higher dimensional matrices that would, become very complicated very quickly. And so, but what I wanted to do, what I was hoping was that there would be a pattern. Okay, so I was hoping that there would be a pattern between the 4-element complex numbers and the 16-element quaternions. And so this was my first guess. This was my first guess. What I wanted was for the 4 big elements to be a complex number in itself. Okay, and so in order for that to be true, the forward diagonal would have to have the same sense. Okay, and then the backward diagonal would have to have the opposite sense. And I was also hoping that each element would somehow be a complex number itself. So this would be sort of the fractal scaling, where this is a complex number and each of these is a complex number, and then as you go higher order you find more complex numbers. So really it's complex numbers under the hood, and I was almost right. Okay, this was my first guess before I even did anything, and it turned out that I was almost right, that these 2 elements here, so the forward diagonal turns out that to be, each one of these turns out to be a complex number, but the backward diagonal is a little different. And so this is what I'm going to show you how I came to this conclusion. But basically I did everything kind of from scratch. What I did was I wrote a little program. So the next thing I needed to do was I needed to find the identities. So analogous to the identities of the complex numbers, where you have just ones and minus ones in the matrix. Okay, I wanted to find the identities for the quaternions using a numerical method. So I wrote a computer program to find all of the identities that satisfied these rules. Okay, so we know that the real number squared has to equal to 1. So I wanted it to satisfy the rules that I set out earlier. So where the real number squared is equal to 1, which is 1s on the forward diagonal, and the imaginary number squared is equal to minus 1s on the forward diagonal. And so that is what I tried to accomplish here. And so trivially, we're going to start with the real. Okay, so for the real identities, the 2 real identities for the quaternions are going to be 1s on the forward diagonal, positive 1s on the forward diagonal. So I'm going to represent that as 1 in square brackets, just like I did for complex numbers, only now we're talking about 4-dimensional numbers. And trivially as well, the minus 1 is going to have minus 1s on every element in the forward diagonal. Okay, so this is plus 1 and this is minus 1 in quaternions. So as I ran my program, I found a bunch more. I found a bunch of identities. Now I needed to find the identities that equaled to -1. So now I had to find the identities that had -1. So when I square them, so the idea here is I squared is equal to -1, J squared is equal to -1, K squared equals to -1. What that means is that when I square the matrix, so I need to find matrix pattern that such that where I square it, it gives me -1s in the forward diagonal. And so the first one that came up was this one here. And I ended up calling that I. Okay, it was arbitrarily, I'm arbitrarily calling it I, but it actually turns out to be the right thing to do. And so when you put a positive 1 here, and a -1 here, and a positive 1 here, and a -1 here, and you square it, you get -1s on the forward diagonal. So that looks like a keeper to me. So I'm going to call that I. And also the negative solution came up, which means that you take the positive and make it negative, you take the negative and make it positive, and just do the same here. When you square this matrix, you take this matrix and multiply it by this matrix, you also get -1s on the forward diagonal. So I'm going to call this I, and I'm going to call this -I. Okay, another one came up, which I'm going to call J. Okay, so when you have plus, plus, minus, minus, plus, plus, minus, minus on the backward diagonal, when you square that, you get negative ones on the forward diagonal. And as well, you get, if you take negative 1, positive 1, positive 1, and you square it, you get negative ones in the backward diagonal, in the forward diagonal. So you get this value right here. So now we've got two identities, a real identity and an imaginary identity for real, for the real component, for this component here. We've got a positive and negative identity for I, this one right here. And we've got a positive and a negative identity for J. So now we need one more. We need one more identity for to represent K. So here is what I found. I found an identity such that we had a positive here and a negative here and a negative here and a positive here. And when you square this, when you multiply this by itself, you get negative ones in the forward diagonal. And when you reverse the sense of all these, so if you make the positives negative and negative positive, so when you have negative 1, positive 1, positive 1, negative 1, then and you square that, you get minus ones along the forward diagonal. Okay, so now we have something for each. We've got the R, we've got the I, we've got the J, and we've got something for K. Okay, so now what I'm going to do is I'm going to put the positive identities on the same page. And so what we found with the complex number, with the two-dimensional complex number, is when you add them, they both can fit in the same matrix. Okay, they both can fit in the same matrix. So the real component goes on the forward diagonal and the imaginary component goes on the backward diagonal, and that's what it means to add these two together. When you add them, you're really just putting them, you're not adding them in the traditional sense, A plus B. What happens is they can coexist in the same matrix. So A is the real component, goes on the forward diagonal. B is the imaginary component and goes on the backward diagonal. So in a similar manner, all these four components, now that we have a 4x4 matrix, these four components have to be such that they can coexist in the matrix. Okay, they can just like we coexist in a matrix, they have to coexist in a matrix. And so the first one here, so what I want you to notice is that the identity for the real numbers, the 1, is on the forward diagonal, and the J here, what I identified as J, is occupying the backward diagonal of the 4x4 matrix. And the I, what I identified as I, they live in these, they occupy these elements in the matrix, and K occupies these elements in the matrix. And so these identities do not overlap at all. They can coexist in the matrix, in the Quaternion 4x4 matrix. And so the A goes in the forward diagonal. Okay, so A, if you multiply A by the identity of the real matrix, of the real component of the 4x4 matrix, then you're going to get A. So you're going to put A's. You're going to put A's in this forward diagonal here. And so now this is I. This is the identity I. So what you do is you multiply B. You put you put a B everywhere there's a 1 here. You replace it with a B. So you're going to get B minus B, B minus B. Okay, B minus B. B minus B, and those are going to go here. B minus B, B minus B. And then for the J, because J goes with C, so when you multiply C by this matrix here, you're going to get a positive C, negative C, negative C. And that's what we see here. Positive C, negative C, negative C. And then finally the K, when you multiply D by this matrix here, by the K matrix. And so the D's are going to go everywhere. So you've got positive 1, negative 1, negative 1, positive 1. Okay, positive D, negative D, negative D, positive D. So this is the complete Quaternion matrix, analogous to the complex matrix, which we saw up here, right? It's just a little bigger, it's got more elements, but it is essentially the same. So as you can see here, the complex matrix, the two-dimensional complex matrix has A, B minus B. And what we find here is that on the forward diagonal of the Quaternion matrix, we've got A, B minus B, A, B minus B. So the Quaternion matrix, at least on the forward diagonal, has a complex number here and a complex number here, and they are the same sense. They are the same sense. So this is a positive, this would be positive complex number with the positive on the forward diagonal and the positive negative here. And this is also a positive complex number with the positive on the forward diagonal and positive and negative here. So I originally said it would be nice if the big matrix is a complex number, but if each of these little ones is a complex number. And this turns out to be true for the forward diagonal, but it is not true for the negative diagonal, because this is not a complex number. And as it stands, this is not a complex number, and this is not a complex number. So my original assessment here was that each element should be a complex number and the big one should be a complex number, and this is all true. Okay, this is sort of true, but the upper right and the lower left are not traditional complex numbers. But what I realized by looking at this a little more closely is if you take, say, this value here in this quadrant here, and you rotate it by 90 degrees. If you rotate this by 90 degrees, then you see that it is in fact a complex number. You've got the C on the forward diagonal, and they are the same sense. And you've got the D on the backward diagonal, but they have the reverse sense. And so this value here, and you can see the same thing with the one down here, only they're negative values. And so you can see that in fact this is kind of true, what I said before. It's kind of true, only you need to rotate this by minus 90 degrees. And you need to rotate this matrix by minus 90 degrees. And then we have the Quaternions. So the Quaternions have a complex number in the forward diagonal, and they're both the same sense. And you have a complex number rotated by 90 degrees. So it's actually rotated counterclockwise by 90 degrees, because I have to rotate it clockwise to get it back to being a complex number. Okay, so this is what we have, and this is what I have to do to get it to a complex number. So this would be the what I'm showing here, the C plus DI. This would be the C plus DI only to get it into quaternion format, this has to be rotated. This matrix needs to be rotated not counterclockwise by 90 degrees. And so now, so this kind of fits my model where the big thing is a complex number because you've got something positive and something positive in the forward diagonal, and you have something positive and something negative in the backward diagonal. And so this would be what we would call a hypercomplex number because it's a complex number in a complex number. As well, we've got this minus 90 degree rotation, which makes sense because this is on the backward diagonal, and in complex numbers, this would be the imaginary component of the big complex number, of the big Q. Okay, so this is a complex number, this is a complex number, this is a complex number, this is a complex number rotated by 90 degrees, and this is a complex number rotated by 90 degrees. And so this kind of fit my idea at the beginning that each quadrant should be a complex number, plus the big thing should also satisfy the rules of complex numbers, and it does because the forward diagonal is the same sense and the backward diagonal is the opposite sense. And so I found this really interesting. My intuition was that complex numbers or quaternions are complex numbers under the hood, only I didn't realize, how beautiful this pattern was, that in fact it's almost a fractal scaling of a complex number because this 4x4 matrix or this 2x2 matrix, the big matrix, is a complex number, and each element under the hood is also technically a complex number. There's one other set of rules that quaternions need to satisfy to actually be quaternions, and that is the set of rules over here. So we've already satisfied the real identities squared must equal to +1, and by +1 I mean positive ones on the forward diagonal of the 4x4 matrix. Each of the imaginary identities, when you square them, also has to work out to -1, which is -1 on the forward diagonal, on each element of the forward diagonal of the complex of the quaternion matrix. There's another one right here, which is I times j times k must also equal to -1, and that comes out of these rules here. So these rules need to be satisfied. So I times j has to equal k. So the identity matrix I times the identity matrix j has to equal the identity matrix K, and the identity matrix J times the identity matrix K has to equal the identity matrix I, and the identity matrix K times the identity matrix I, that's supposed to be a small I, is supposed to equal the identity matrix J. And when you swap these, so I times j equals k, j times I, little I, equals minus k. Okay, and j times k equals I, and k times j equals minus I. And minus I just means that all the elements in the matrix are negative compared to the positive version. And so I'm not going to actually do this here because it is kind of boring, but I can tell you that when I multiply this matrix here by this matrix here, I get this matrix here. And when I multiply this matrix here, so j times I, I'm going to get negative here and positive here and positive here and negative here. So I'm going to get negative k. And the same with all the other identities. So I did this using a program that I will link in the description where you can enter values into the matrix and you can multiply them and see what the answer is but I'm not going to do that because I've already done it and I've proven it's true, and so I will leave that as an exercise to the viewer to do this to prove that what I'm saying is correct and that these are in fact the correct identities for I, positive J, and positive K. Here's where it gets really interesting. Okay, so I'm going to walk you through a little thought experiment that I did, and it turned out to be an actual experiment that I did. And so we're going to start with the complex number. I'm going to invent a little terminology here. I'm going to call this a Quaternion because of the Quaternion. Okay, so the Quaternion has two elements in the row and two elements in the column. It is a 2 by 2 matrix, and it is of this form. Okay, the Quaternion is a 4 by 4 matrix. Okay, it's a 4 by 4 matrix, and it contains the Quaternions, the complex numbers, in the forward diagonal and the backward diagonal, only these ones are rotated by minus 90 degrees. And so what if I wanted to do an octernion? And so the octernion would be an 8 by 8 matrix. So what I'm going to do is I'm going to apply the same procedure, the same formula that I applied to get from complex numbers to quaternions, to get from quaternions to octernions. Okay, and so to get from complex numbers to quaternions, what I found was that you put the complex number on the forward diagonal with the same sense, and you put the complex number as if this was a complex number on the backward diagonal, but you rotate it by minus 90 degrees. And so the question I had was, can I do this again? So instead of taking the complex number, I'm going to take the quaternion and I'm going to put it on the forward diagonal of the octernion matrix. And then I'm going to take the quaternion and I'm going to put it on the backward diagonal as is. So I'm going to replace A with E, B with F, D with H, and C with G. And then I'm going to rotate this counterclockwise by 90 degrees. Okay, so I'm going to do the same procedure that I did to get from complex numbers to quaternions to get from quaternions to octernions. Okay, so I'm going to write this down properly so you can see that I've got G minus H F E, G minus H F E. So I've rotated the matrix, and now this is the, okay, I'm going to just copy and paste this here because I forgot. This is the octernion matrix. Okay, this is the octernion matrix according to the formula that I discovered. I'm going to say I discovered it because I didn't read about it, I didn't find it, nobody else that I know of has taught this or done it this way, and so using this procedure of to get from complex numbers to quaternions, I used to get from quaternions to octernions, and this turns out to be correct. Okay, this turns out to be correct. And so I tested all the identities. So the real identity is on the forward diagonal. So this whole thing now is an 8 by 8 matrix. Okay, this is a quaternion, and this is a quaternion, and this is a quaternion, only it was rotated minus 90 degrees. And this is a quaternion, only it was rotated minus 90 degrees. And so these two on the forward diagonal have the same sense, and these two on the backward diagonal have the opposite sense. So this is technically a complex number, at the very least, it satisfies the rule of forward and backward diagonal that I enforced, or that I suggested for the complex numbers. So that is the rule that I showed you at the very beginning. Okay, the forward diagonal has the same sense, and the backward diagonal has the opposite sense. And so that is the case for the octernion, that is the case for the quaternion, and that is also the case for the original complex number. So I found this very interesting, actually, and I think that this has sort of profound meaning, at least it does to me, because I can apply. Now this has way too many degrees of freedom. This is completely, I'm going to say not completely unnecessary, but in regards to doing three-dimensional graphics in three-dimensional space where you have three angles that you have to keep track of, quaternions suit this purpose. Okay, so quaternions are fine just the way they are. You don't really need octernions for anything practical, but in terms of a mathematical construct, it is, it's a really interesting construct. And of course, you could apply this again. You could take the octernion and take this whole thing and put it in the forward diagonal of a 16 by 16 matrix, and we're going to start to run out of letters of the alphabet if I do that. I'm not going to do that, but you can apply the same procedure and get a super hyper complex number, which is a complex number and a complex number and a complex number, this procedure will work. Okay, so you can get super hyper complex numbers by following the procedure that I showed you, and you don't even really have to do any math. Okay, this is just a computer algorithm that could iterate this over and over again and get a super complex number with matrices that are very, very large. So whether it's useful or not, I don't know, but this is a nice way of getting hypercomplex numbers without having to do any algebra. In the next video, I'm going to show you how to use the Quaternion 4x4 matrix. This can be used directly, just like I use complex numbers to generate the Mandelbrot set. So with the complex numbers, I was generating a two-dimensional Mandelbrot set, but using the quaternions just as is, using this matrix directly, I can now generate the Mandelbrot set quite easily in 4 dimensions. Now it is impossible to visualize 4 dimensions. I have to do some tricks in order to visualize the 4-dimensional Mandelbrot set, but this is really interesting. This is a way of visualizing quaternions. Once you see the 4-dimensional Mandelbrot set, you're going to get, I think, a better feel for what the quaternion really is. And so I'm going to leave this as is. This video is getting quite long, and so I'm going to leave it as is, and you will have to wait for the video I make on the Quaternion Mandelbrot set, which I really look forward to making. I actually did this many years ago using the algebraic version of quaternions. This is the first time, this weekend was the first time that I used this matrix format to directly generate the Mandelbrot set, and it was super simple. And so I will show you the code for that as well. So thank you very much, and I hope you guys all have a great week.